Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Could Antarctica become the next supercontinent? Part 1. The frozen frontier of geological destiny. In the vast white expanse of Antarctica, where silence reigns and ice tells stories billions of years in the making, a profound geological drama is unfolding. Beneath the pristine surface of the southernmost continent lies a narrative of planetary transformation that challenges our most fundamental understanding of Earth's geological future. The concept of continental drift, once a radical theory, now stands as a cornerstone of modern geological science. Plate tectonics reveals our planet as a dynamic, ever-changing system where continents are not static monuments, but wandering giants reshaping themselves across unimaginable timescales. Antarctica, often perceived as a frozen wilderness, is actually a critical character in this ongoing planetary narrative. Geologists and paleontologists have long understood that continents are not permanent fixtures. They collide, separate, and reconfigure in a dance that spans hundreds of millions of years. The supercontinent cycle, a rhythmic process of continental aggregation and dispersal, has sculpted Earth's surface multiple times. Pangaea, the most recent supercontinent, began breaking apart approximately 220 million years ago, setting the stage for our current continental configuration. But what makes Antarctica unique in this geological saga? Its position, at the bottom of the world, combined with its complex geological history, suggests it might play a pivotal role in the next great continental reassembly. The Antarctic tectonic plate sits at a crucial intersection, surrounded by the Pacific, Atlantic, and Indian Ocean plates, a strategic location that hints at its potential future significance. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Modern scientific instruments and satellite technologies have revolutionized our ability to track continental movements. Geodetic measurements using GPS technology can now detect plate movements with millimeter-level precision. These technologies reveal that Antarctica is not as stationary as its icy facade might suggest. Subtle but consistent movements indicate the continent is slowly but inexorably changing its position. The Antarctic continent is a geological palimpsest, with rock formations that tell stories of past configurations. Researchers have discovered geological signatures that link Antarctica to other continents, suggesting its role in previous supercontinental formations. The Transantarctic Mountains, a massive mountain range bisecting the continent, preserve geological records that provide critical insights into these ancient transformations. Climate plays a crucial role in this potential future reconfiguration. As global temperatures shift, the massive ice sheets covering Antarctica are changing, revealing geological features that have been hidden for millions of years. These emerging landscapes offer geologists unprecedented opportunities to study the continent's tectonic potential. Plate tectonics operates on timescales that dwarf human comprehension. While we might perceive continents as fixed and immutable, they are actually in constant, albeit incredibly slow, motion. Antarctica's current position is merely a snapshot in a much longer, more complex geological narrative. The forces that will potentially reshape it into a future supercontinent are already in motion, operating with a patience that makes human timescales seem ephemeral by comparison. As we stand on the precipice of understanding these monumental planetary processes, Antarctica emerges not just as a frozen continent, but as a dynamic geological actor with the potential to rewrite Earth's continental story. The next chapters of this narrative are yet to be fully understood, promising discoveries that will challenge and expand our comprehension of planetary evolution. Could Antarctica become the next supercontinent? Part 2. The geological heartbeat of a changing planet. Imagine a planet breathing, not with lungs, but with tectonic plates. Each movement is a slow, almost imperceptible pulse that reshapes continents over millions of years. Antarctica sits at the center of this planetary heartbeat, a geological time capsule that holds the keys to understanding Earth's most profound transformations. The story of continental evolution is written in the language of plate tectonics, a scientific theory that emerged in the 1960s, revolutionizing our understanding of planetary dynamics. At the heart of this theory lies the concept of plate boundaries, regions where tectonic plates interact in a complex dance of convergence, divergence, and transformation. Antarctica's unique geological position makes it a critical player in this global drama. Subduction zones, where one tectonic plate slides beneath another, are the primary engines of continental reconfiguration. The Antarctic plate interacts with several surrounding plates, including the Pacific plate, the South American plate, and the Australian plate. These interactions create a complex geological tapestry that hints at future continental possibilities. The Scotia Plate, a microplate nestled between South America and the Antarctic Peninsula, serves as a prime example of the intricate plate interactions that could eventually lead to a new supercontinent formation. Geophysicists use advanced technologies to map these movements with unprecedented precision. Seismic tomography, a technique that creates three-dimensional images of Earth's interior using seismic wave data, reveals the hidden landscapes beneath the continent's icy surface. These images show a complex network of geological structures, including ancient mountain roots, subducting plates, and potential future collision zones. The concept of the next supercontinent, often referred to as Pangaea Ultima or Amasia, is not mere speculation, but a serious scientific hypothesis. Researchers at leading institutions like the AGU, American Geophysical Union, and various international research centers have been modeling potential future continental configurations. These models suggest that Antarctica could play a pivotal role in the next great continental assemblage. Paleomagnetic studies provide crucial evidence for continental movement. By analyzing the magnetic signatures locked in rock formations, scientists can track the movement of continents over hundreds of millions of years. Antarctic rock formations contain some of the most valuable paleomagnetic data, offering insights into the continent's journey through geological time. The Antarctic continent is anything but a static mass of ice. Beneath its frozen exterior lies a geologically active landscape with mountain ranges, volcanic systems, and tectonic boundaries that tell a story of constant change. The Transantarctic Mountains, stretching over 3,000 kilometers, represent a geological boundary that marks the transition between two fundamentally different geological provinces. Climate change adds another layer of complexity to this geological narrative. As global temperatures rise, the Antarctic ice sheets are retreating, revealing geological features that have been hidden for millions of years. This unprecedented exposure provides researchers with new opportunities to study the continent's geological history and potential future. Volcanic activity beneath the ice offers additional clues to Antarctica's geological potential. The West Antarctic Rift System, a complex network of geological fractures, demonstrates the continent's ongoing tectonic activity. Mount Erebus, an active volcano located on Ross Island, serves as a visible reminder of the dynamic geological processes continuously shaping the continent. The story of Antarctica is far from complete. Each scientific expedition, each core sample, each satellite measurement adds another piece to the complex puzzle of continental evolution. As we stand on the brink of understanding these massive planetary transformations, Antarctica emerges as a living, breathing testament to the dynamic nature of our planet, a frozen continent holding the secrets of Earth's geological future. Could Antarctica become the next supercontinent? Part 3. The geological architects of continental transformation. In the realm of planetary sciences, time is not measured in seconds or minutes, but in epochs that stretch far beyond human comprehension. The journey of a continent is a narrative written in the language of geological processes, a story of immense forces, slow transformations, and planetary rebirth that challenges our most fundamental understanding of Earth's dynamism. The supercontinent cycle represents a fundamental rhythm of our planet's geological heart. Over the past 2 billion years, Earth has witnessed at least 5 major supercontinent configurations. Pangaea, the most recent, was not an anomaly but part of a recurring planetary pattern. Scientists now understand that continents are not permanent fixtures, but temporary arrangements in a cosmic dance of tectonic plates. Plate tectonics reveals a counterintuitive truth. What appears solid and immutable is actually in constant, albeit imperceptible, motion. The Antarctic plate moves approximately 2 to 4 centimeters per year, a speed comparable to the rate at which human fingernails grow. Yet over millions of years, this seemingly insignificant movement can reshape entire planetary landscapes. The geological potential of Antarctica is deeply rooted in its complex tectonic history. The continent sits atop a unique geological crossroads, surrounded by the Pacific, Atlantic, and Indian Ocean plates. This strategic position makes it a critical piece in the puzzle of future continental configurations. Researchers use advanced geophysical techniques to map the intricate network of fault lines, subduction zones, and geological boundaries that crisscross the continent. Seismic tomography provides unprecedented insights into the continent's subsurface structure. By analyzing seismic wave propagation, scientists can create three-dimensional images of the geological layers beneath Antarctica's icy surface. These images reveal a complex landscape of ancient mountain routes, potential collision zones, and hidden geological features that tell a story of planetary transformation. The formation of a new supercontinent is not a sudden event, but a gradual process that unfolds over hundreds of millions of years. Current scientific models propose several potential scenarios for the next supercontinent. The leading hypotheses include Pangaea Ultima, Amasia, and Nova Pangaea, each presenting a different vision of how the world's continents might ultimately reunite. Paleomagnetic research plays a crucial role in understanding continental movement. By analyzing the magnetic signatures preserved in rock formations, scientists can track the journey of continents across geological time. Antarctic rock formations are particularly valuable, containing some of the most detailed records of planetary movement. Each rock layer is a page in Earth's geological manuscript, preserving memories of ancient landscapes and tectonic interactions. Climate change adds another layer of complexity to this geological narrative. As global temperatures rise, the retreating Antarctic ice sheets are revealing geological features that have been hidden for millions of years. This unprecedented exposure provides researchers with new windows into the continent's geological history and potential future. The West Antarctic Rift System, a complex network of geological fractures, offers particularly tantalizing insights into the continent's tectonic potential. Volcanic activity beneath the ice provides additional evidence of ongoing geological processes. The subglacial volcanoes of Antarctica, some of which remain active beneath miles of ice, demonstrate the dynamic nature of the continent's geological systems. Mount Erebus, the southernmost active volcano on Earth, serves as a visible reminder of the powerful geological forces continuously reshaping the continent. The story of Antarctica is far from complete. Each scientific expedition, each core sample, each satellite measurement adds another piece to the complex puzzle of continental evolution. As we stand on the brink of understanding these massive planetary transformations, Antarctica emerges as a living testament to the dynamic, ever-changing nature of our planet, a frozen continent holding the keys to Earth's geological future. Could Antarctica become the next supercontinent? Part 4. The hidden mechanisms of continental transformation. Beneath the pristine white landscape of Antarctica lies a geological orchestra of unprecedented complexity. The mechanisms driving continental transformation are as intricate as they are powerful, a symphony of geological forces that operate on timescales far beyond human perception, yet ultimately reshape our entire planet. The primary engine of continental movement is mantle convection, process as elegant as it is violent. Deep within Earth's interior, temperatures can reach up to 5,400 degrees Celsius, creating massive circular currents of molten rock. These currents act like a planetary conveyor belt, slowly but inexorably moving tectonic plates across the globe. Antarctica sits at a critical junction of these massive thermal currents, making it a pivotal player in the global geological system. Subduction zones represent the most dramatic manifestation of these geological processes. Here, one tectonic plate is forced beneath another in a slow-motion collision that can generate tremendous geological energy. The boundary between the Antarctic plate and the surrounding plates, particularly the Pacific and South American plates, creates a complex zone of interaction that could potentially trigger massive continental reorganization. Advanced geophysical technologies have revolutionized our understanding of these processes. Satellite-based GPS measurements can now track plate movements with millimeter-level precision. Interferometric synthetic aperture radar, or INSAR, allows scientists to measure microscopic changes in land surface, revealing the subtle movements that hint at future continental configurations. The concept of continental drift, once considered a radical theory, now stands as a fundamental principle of Earth sciences. Pioneering work by researchers like Alfred Wegener in the early 20th century laid the groundwork for our current understanding. Wegener's hypothesis of continental drift was initially met with skepticism, but subsequent discoveries in paleomagnetism, seafloor spreading, and plate tectonics have transformed it into a cornerstone of geological science. Antarctica's geological complexity extends far beyond its surface. The continent is home to some of the most diverse and ancient geological formations on the planet. The Transantarctic Mountains, stretching over 3,000 kilometers, represent a geological boundary that tells a story of millions of years of planetary transformation. These mountains are not merely a physical barrier, but a living record of Earth's geological history. Paleomagnetic research provides crucial insights into continental movement. By analyzing the magnetic signatures locked in rock formations, scientists can reconstruct the journey of continents across hundreds of millions of years. Antarctic rock formations are particularly valuable, containing some of the most detailed and well-preserved geological records on the planet. The potential for Antarctica to become a future supercontinent is rooted in its unique geological position. Current scientific models propose several scenarios for continental reassembly. The hypothesis of Pangaea Ultima suggests that over the next 250 million years, the world's continents might gradually converge, with Antarctica playing a central role in this massive geological reconstruction. Volcanic activity beneath the ice offers additional evidence of the continent's geological dynamism. The West Antarctic Rift System demonstrates ongoing tectonic processes that could ultimately contribute to continental transformation. Subglacial volcanoes, some hidden beneath miles of ice, provide tangible proof of the powerful geological forces continuously reshaping the continent. Climate change adds another layer of complexity to this geological narrative. As global temperatures rise, the retreating Antarctic ice sheets are revealing geological features that have been hidden for millions of years. Each newly exposed rock formation, each geological boundary, tells a fragment of a much larger story, a story of planetary transformation that continues to unfold beneath our feet. Could Antarctica become the next supercontinent? Part 5. The technological frontiers of geological exploration in the most remote and challenging environment on our planet. Science pushes the boundaries of human knowledge with technologies that transform our understanding of geological processes. Antarctica stands as the ultimate proving ground for technological innovation, where cutting-edge research meets the most extreme conditions imaginable. Satellite technologies have revolutionized our ability to study continental movement with unprecedented precision. The IRIS Intergovernmental Reference Instrument System provides millimeter-level measurements of plate movements, capturing the slow dance of continents that was once invisible to human observation. These technological marvels can detect ground displacement as small as 2 millimeters, a movement so subtle it would go unnoticed by the human eye, yet significant enough to reveal the fundamental mechanisms of planetary transformation. Seismic. Tomography represents a quantum leap in geological imaging. By analyzing the propagation of seismic waves through the Earth's interior, scientists can create three-dimensional maps of the planet's subsurface structure. These technological windows allow researchers to peer deep into the planet's interior, revealing the complex network of geological structures that drive continental movement. The Antarctic continent provides a unique laboratory for these advanced imaging techniques, with its relatively undisturbed geological formations offering pristine data. Artificial intelligence and machine learning have become critical tools in geological research. Advanced algorithms can now process massive datasets from satellite observations, seismic measurements, and geological surveys, identifying patterns and potential future configurations that would be impossible for human researchers to detect. These computational models can simulate continental movement over hundreds of millions of years, providing insights into the potential future of Earth's geological landscape. The challenges of Antarctic research are formidable. Temperatures can plummet to negative 89 degrees Celsius, with wind speeds reaching up to 300 kilometers per hour. Yet, despite these extreme conditions, an international community of researchers continues to push the boundaries of scientific exploration. Specialized research stations like the Antarctica, Advanced Navigational Technologies and Research Center for Innovative Continental Analysis, serve as technological outposts at the edge of human knowledge. Drilling technologies have opened new frontiers in geological exploration. Deep ice cores extracted from the Antarctic ice sheet provide a remarkable climate and geological record stretching back hundreds of thousands of years. These cores are more than just scientific samples. They are time capsules that preserve detailed information about our planet's geological and climatic history. Robotic exploration has become increasingly crucial in Antarctic research. Autonomous underwater vehicles and advanced ground-penetrating radar systems can navigate beneath the ice, mapping subglacial landscapes and geological formations that have remained hidden for millions of years. These technological marvels can explore regions that would be impossible for human researchers to access, revealing the hidden geological architecture of the continent. Paleogenetic research adds another dimension to our understanding of continental transformation. By analyzing genetic markers preserved in ancient biological materials, scientists can reconstruct the geological and biological history of the continent. These studies reveal how geological processes have influenced biological evolution, creating a more comprehensive understanding of planetary change. The integration of multiple scientific disciplines creates a holistic approach to understanding continental dynamics. Geologists, climatologists, physicists, and computer scientists work together, combining their expertise to unravel the complex mechanisms of planetary transformation. Antarctica serves as the ultimate interdisciplinary laboratory, where the most advanced technologies converge to explore the fundamental processes that shape our planet. As technology continues to advance, our understanding of continental movement becomes increasingly sophisticated. Each new technological breakthrough brings us closer to comprehending the grand narrative of planetary evolution, a story written in rock, ice, and the subtle movements of massive geological plates. Could Antarctica become the next supercontinent? Part 6. The biological and climatic dimensions of continental transformation. Beyond the realm of pure geology, the potential transformation of Antarctica into a future supercontinent reveals a complex interplay of biological adaptation, climate dynamics, and planetary evolution. The story of continental movement is not just a tale of rocks and plates, but a profound narrative of life's resilience and adaptation. Climate models suggest that the formation of a new supercontinent would trigger massive global environmental transformations. As continents converge, ocean currents would be dramatically altered, reshaping global weather patterns, atmospheric circulation, and biological ecosystems. The potential configuration of Pangaea Ultima or Amasia represents more than a geological hypothesis. It is a potential future that could fundamentally reshape life on Earth. Paleontological evidence demonstrates the profound impact of continental configurations on biological evolution. During the formation of previous supercontinents, massive environmental changes drove unprecedented biological diversification and extinction events. The boundaries between continents, known as suture zones, become crucibles of evolutionary innovation, where isolated ecosystems collide and new biological interactions emerge. The Antarctic ecosystem provides a unique window into the resilience of life under extreme conditions. Microorganisms discovered in the continent's most extreme environments, including subglacial lakes and volcanic regions, challenge our understanding of biological adaptation. These extremophiles represent living laboratories of survival, offering insights into how life might persist and evolve during massive planetary transformations. Genetic research has revealed remarkable connections between Antarctica and other continents. Fossil records and genetic markers demonstrate that the continent was once part of a massive southern landmass called Gondwana, which included present-day South America, Africa, India, Australia, and New Zealand. These genetic threads tell a story of biological migration and adaptation that spans hundreds of millions of years. Climate change accelerates our ability to observe geological and biological transformations. As Antarctic ice sheets retreat, researchers are discovering ecosystems that have been isolated for millions of years. Subglacial lakes like Lake Vostok, a massive body of water buried beneath 4 kilometers of ice, represent entire ecosystems that have been completely cut off from the outside world for potentially millions of years. The potential formation of a new supercontinent would trigger massive changes in global biodiversity. As landmasses converge, biological barriers would be removed, creating unprecedented opportunities for species migration and interaction. The collision of different evolutionary trajectories could spark waves of speciation, driving biological innovation on a planetary scale. Computational models now allow scientists to simulate not just geological movement, but the potential biological and climatic consequences of continental reconfiguration. These models integrate data from multiple scientific disciplines, geology, climatology, biology, and computer science, to create comprehensive projections of planetary transformation. The West Antarctic Rift System offers a living laboratory for understanding these complex interactions. This geological feature demonstrates how tectonic processes, climate dynamics, and biological adaptation are deeply interconnected. The ongoing geological processes in this region provide tangible evidence of the dynamic nature of our planet. We stand at the precipice of understanding these massive planetary transformations. Antarctica emerges as more than just a continent. It is a living testament to the interconnectedness of geological, climatic, and biological systems, a frozen archive of planetary history, and a window into the potential future of life on Earth. Could Antarctica become the next supercontinent? Part 7. The cosmic perspective of planetary transformation. In the grand tapestry of cosmic evolution, the transformation of Antarctica into a future supercontinent represents more than a geological event. It is a profound meditation on the nature of planetary change, scientific exploration, and humanity's place in the universe. Our understanding of continental movement transcends mere physical description, touching the deepest questions of planetary dynamics and cosmic transformation. The supercontinent cycle is a rhythm as old as our planet itself. Over the past 2 billion years, Earth has witnessed at least 5 major continental configurations, each representing a unique moment in planetary evolution. The movement of continents is not a random process, but a systematic dance governed by fundamental physical laws that operate across unimaginable timescales. Antarctica stands as a critical node in this planetary choreography, a frozen sentinel holding the memories of countless transformations. Current scientific models propose multiple scenarios for future continental configurations. The hypothesis of Pangaea Ultima suggests that over the next 250 million years, the world's continents might gradually converge into a new supercontinent. Another model, known as Amasia, predicts the potential merger of the North American and Asian continents, with Antarctica playing a pivotal role in this massive geological reconstruction. The technological and scientific advancements that allow asked to contemplate these future configurations represent a quantum leap in human understanding. Satellite-based GPS technologies, advanced seismic tomography, and sophisticated computational models have transformed our ability to peer into the planetary future. What was once the realm of speculation has become a rigorous scientific discipline, capable of modeling continental movements with unprecedented precision. Interdisciplinary research has been crucial in developing this comprehensive understanding. Geologists, climatologists, biologists, and computer scientists collaborate to create holistic models of planetary transformation. Each discipline contributes a unique perspective, revealing the intricate interconnections between geological processes, climate dynamics, and biological evolution. The story of Antarctica is ultimately a story of resilience and transformation. From its position as part of the ancient Gondwana supercontinent to its current isolated state, the continent has been a witness to billions of years of planetary change. Subglacial lakes, hidden volcanic systems, and ancient rock formations serve as living archives of this remarkable history, preserving memories of planetary processes that stretch far beyond human comprehension. Climate change accelerates our ability to observe and understand these transformations. As Antarctic ice sheets retreat, researchers gain unprecedented access to geological features that have been hidden for millions of years. Each exposed rock formation, each newly discovered geological boundary, tells a fragment of a much larger story, a narrative of planetary evolution that continues to unfold. The potential future of Antarctica as a supercontinent represents more than a scientific hypothesis. It is a profound meditation on the dynamic nature of our planet, a reminder that the Earth is not a static entity, but a living, breathing system of incredible complexity. The movements of continents occur on timescales that dwarf human experience, yet they are fundamental to understanding our planetary home. As we stand at the threshold of this profound understanding, Antarctica emerges as a symbol of planetary potential. It is a frozen continent that holds the keys to understanding the past, present, and future of our planet. Each scientific expedition, each technological breakthrough, brings us closer to comprehending the grand narrative of planetary evolution, a story written in rock, ice, and the subtle movements of massive geological plates that connect us to the deepest rhythms of cosmic change.